So last time, I think we were here, right? We are talking about TLBs. Let me go. We have CPU generating virtual address, TLB translation group aside order. That is doing translation, right? And TLB hopefully provide physical address. And based on that, you are accessing main memory. So that is main memory. Okay, and you have hard disk. Hard disk or solid state drive these days. And cache is somewhere, right? Cache is depending on CPU vendor, and cache could be placed here or here. Cache can be placed here, and using virtual address to access, or can be placed here. So using cache can be accessed with physical address. It depends on implementation. So let's remove. Let me remove this one because we want to focus on address translation in this class. Only address translation. On PC. So virtual space, depending on this address size, if it is 32, then virtual space size is 4 gigabyte, right? 2 to the power of 32, right? And physical address space, depending on this physical address. So physical address, the width is 36 bit. For example, if it's 36 bit, then you are creating public space, physical space, 2 to the power of 36, then 64 gigabyte physical space. Then actual main memory can be placed within that physical space. So let me do it. So 6-bit physical address is creating this physical space. As the name implies, a space, right? Space. Actually, nothing is there. The beginning. Physical space. And then motherboard designer, computer motherboard, right? Making that decision on where to place actual main memory. Okay. You are creating 64 gigabyte physical space. Then probably you want to place 3216, probably 16 gigabyte physical actual main memory here. So you are only consuming, you are using only that 1/4, right? 1/4 of this, 1/4 of this space. Right? So it is motherboard manufacturer is doing that, right? 16 gigabyte actual memory. So what I want to do is, so let me now remove. And then just put 16 gigabyte maybe. Then this virtual space and physical memory is logically divided into typically 4 kilobytes. 4 kilobytes. 4 kilobytes. This one also 4 kilobytes. 4 kilobytes. And Then you want to do this, right? This one is virtual page number 0, virtual page number 1, and so on. Then the last one, virtual page number 1. 1 million minus 1. So million is 1024 square. 1024 square. And then you want to do this. Okay, the first virtual page is actually located. So this one is probably physical page number 16 gigabyte divided by 4K. How big? 4 meg, right? 4 meg different physical pages. So probably 2 meg physical page number 2 meg. So this one, second virtual page is mapped to physical page number 1 million. Something like this. Operating system is doing this mapping OS. Right? And for that, OS need to create page table. Page table in main memory. Let me draw page table separately. That is located in main memory. Let me draw here. Same color, right? Blue. That is also memory. So inside the memory, you are not you. The operating system is creating page table. So page table is composed of what? PTE. Page table. Page table is composed of page table entries, right? Entry. First entry, second entry, and so on. So how many entries you need? Because you have 1 million virtual pages, you need 1 million entries. So first entry contains the translation information for first one, for virtual page number 0. This one, virtual page number 0. So what you have to have inside here, you need what? Physical page number. That's what you need to have inside the PT. So in this case, this one is mapped to 2 million. Right? So what you have to have is 2 million. And second entry contains translation information for virtual page number 1. So in this mapping, that is mapped to physical page number 1 million. So what you have to have is 1 million. Physical, this one is physical page. The operating system is creating that page to execute your application code. And then what is TLB list? TLB list is what is TLB first? TLB is small cache. Small cache for storing recently accessed page table entries. If you access this one, then TLB contains that information. That 1 million. Some tag information. So virtual page, not for virtual page number, but some part, some of virtual page number. So if you remember, it's a TLB structure. TLB stores not only physical page number, but some of this upper part of virtual page number, except 16 bit. So except this index bit. In this case, 3 bit is used to index TLB. So remaining 17 bit. 17 bit is stored in TLB. So again, TLB is a small cache for storing recently accessed page table entities. So what if So you execute CPU, your program execute LDR or SDR, memory read or write instruction. Then virtual address is generated based on say R0, R1. Let's say R1 is 2000. Then you want to read what from location 2000. So virtual address 2000 will be provided to TLB. So TLB is doing the lookup, TLB lookup, to see if TLB contains the translation information. So TLB has translation information for the TLB hit. Then TLB can provide, physical address. But what if TLB does not contain translation information? That is called the TLB miss. In TLB miss, there are two cases. Simple TLB miss. Simple TLB miss is the page you want to access. The page, let's say the virtual page number 3. This one is not located in main memory. That is still in hard disk. So if TLB does not contain translation information, TLB will miss. But if the page you are accessing, let's say virtual page number 0, virtual page number 0 is already placed in main memory. Okay. So that is simple TLB miss. All you have to do is then, there is translation information. You have to look up page table, then find PTG, and place that guy into here. Place that into here. That's it. That is a simple TLB miss. Again, simple TLB miss means the page you want to access is already present, already in main memory, already loading from hard disk to main memory. So all you have to do is you need only translation information. So look up this page table and place into here. That's what you have to do. Simple TLB miss. Simple, merely TLB miss. And what is page fault? Page fault is this case. So let's say you execute some instruction and happens to access some location in virtual page number 3. Then that virtual page number 3 is not located in main memory. It is in hard disk. All you have to do is, it's very complicated process. It takes a lot of time. But hard disk is so slow. Right? So you have to place that guy into somewhere, some empty slot. They copy the page into main memory. And also translation information. After that, translation information should be placed. So two things: copy page in hard disk into main memory, and that information in the TLB. That is taking a lot of time. And what process you have to go through in case of page fault? Next one. Please. first, TLB is first, right? How TLB is, simple TLB is handled. That is typically handled by hardware. And depending on CPU, CPU is providing option. You can do it. You can handle that. Actually, that is exception case. TLB is that is exception, one kind of exception. Right? So I told you there are two kinds of very important events in CPU: interrupt and exception. In exception, we have studied undefined, very simple case, undefined instruction. And TLB is one kind of exception. If TLB miss happens, you execute LDR instruction. LDR, then R0, R1. Then if you think about pipelining, instruction patch. During instruction patch, TLB miss can happen. You are reading instruction, right? So you have a program counter. Then LDR instruction, let's say it is located at what? Located at which location? 50. 50. Then 50 virtual address is provided to TLB, right? And TLB lookup should be performed, right? And TLB lookup, it turns out to be TLB miss. Okay? Then exception. Then what should happen? So the exception can be handled by hardware or software. If that is handled in software, if you remember interrupt discussion, look at this. That is called pre-patch abort. Pre-patch abort. Program counter will be changed to 0C. Pre-patch abort. Pre-patch abort. But that is very complicated process, right? So you have TLB miss, then you have an exception, then program counter. Program counter will be changed to 0.8, right? So branch some instruction, right? Branch of pre-patch handler, right? Yeah. That will be executed. Right? So after. So your hello world program, right? And LDR instruction. You have pre-patch abort. Pre-patch abort. Then ISR. Exception service routine. Then you have to come back. When you come back, then you have to re-execute. You have to re-attempt, right? Re-execute that. That you have to re-patch that instruction. You haven't executed that instruction yet. You have to start from there. And in case of hardware resolving mechanism, if exception TLB miss is handled by hardware, that is the typical case. Most of CPU vendors are providing hardware-based mechanism to resolve that simple TLB miss. Intel x86 and ARM also. So that is processor. Cortex A9. And then inside this Cortex A9, we have a system register called translation table base register. I'm trying to explain how the entry you are looking for it can be found by hardware and placed into TLB. It is very simple, hardware register. So TTBR register, translation table. This is translation table, right? Translation table base register. So that register should be programmed beforehand. So operating system create this page table and program this register. Let's say that location is 1,000. 1 million. 5 times. So 1 million. So then that should be programmed to 1 million. So that is pointing that location, the base location. Okay. So then CPU knows the start location of page 10. Then what you have to do is, based on this virtual address, based on that this virtual address 50, you need to find out which entry is the one you are looking for. So the indexing scheme is very simple. So you have 1 million virtual pages, right? You have 1 million entries. 1 million virtual pages, 1 million entries. So indexing from this to offset, that information is contained in virtual page number. So virtual address. Start with virtual address. We are assuming 4K byte page size. So last 12 not used. And then upper 20 bit is virtual page. Virtual page number 0, virtual page number 1, and so on. The 4K byte page. 2 to the power of 12, right? So last 12 bit is talking about which data you are looking for within this page. So that's virtual page number. So this offset, the PTE you are looking for can be indexed by virtual page number. So the formula is this, right? So TTDR plus virtual page number. Virtual page number. That is the entry. That is the entry you are looking for. But depending on the PTE size. In case of ARM Cortex A9, PTE, each PTE is 4 byte in size. 4 byte. We are going to talk about the detailed format of this PTE today. So PTE, each PTE is 4 byte in size. That means in this formula you have to do multiplied by 4. Okay. First entry, offset 0. Second entry, offset 4, 8, C, and so on. So based on virtual page number, you are indexing PTE, but you have to do multiplication by 4. Okay. Then how to do multiplication? It's a very simple process. What you can do is VPN left to be left to shift. That's what hardware is doing. Very simple operation. 2 bit left to shift. That is the same effect. So multiplying this number by 2. So the CPU, by implementing this shifter and adder, on adder, right? Adder and shifter. And CPU can pinpoint, okay, location is this one, some entry. Then read that entry from memory and place into TLB. That is called hardware-based page table walk. Hardware-based page table walk. You have a page table and you want to find out PTE. That is typically provided. Any questions so far? Okay, how about page fault? Page fault is taking a lot of time. Very complicated process. Let's assume while you are accessing this memory location, fetch, decoding, execution, memory access, and write back. But during this memory access stage, right? So let's say R1 is 1000. So you are generating 1000 virtual address. So not same address. This virtual address for instruction fetch. So separate collection. That is virtual address for instruction fetch for memory access. Okay. So you are generating 1000. So you have separate. Typically, you have separate TLB. This TLB is for instruction. TLB for instruction, and this TLB is for data. Typically, CPU is providing separate TLB for instruction access, and data access, instruction read and data access. So during memory access stage, assume that you have a page fault. Then what do you want to do? You have to access page fault, right? That means the page in hard disk should be placed in main memory. That is taking millions of clock cycles. Roughly, it takes some few milliseconds to copy that guy into main memory. So that is translated to millions of clock cycles from CPU to memory. So that is running at 4 gigahertz. 4 gigahertz millisecond, right? So if you compare that number, then roughly 4 million clock cycles to resolve page fault. Then you don't want to, right? You don't want to CPU from CPU point of view. You don't want to sit and wait until page fault is resolved, right? So do you want to do this? Memory access, right? That is 4 million clock cycles. Then like that. So you don't want to do that, right? You don't want to wait 4 million clock cycles, right? So that is the operating system is involved. So you have a page fault, then that is the process the operating system is doing. Operating system. So actually, second bullet, a virtual address. This virtual address 1000. 1000 is recorded in some register, fault register, some fault register. CPU is providing some special register to store that information. Okay, we have a page fault while accessing that memory location. Better to show you in example probably. So that is our next lecture or point. Down. Data fault address register. In case of Cortex A9, in case of ARM CPU is providing this register, data fault, right? Data fault, right? You have a data fault while accessing the memory location, page fault, data fault, and that information is stored in that register. Okay. For instruction access, right? So instruction fault, right? Instruction fault address register. While during instruction fetch, LDR, during instruction fetch, you got page fault. Then that virtual address is stored in that register, okay, by hardware. So second bullet, right? Faulting address. The faulting address is already stored in some special register. So based on that, you can find out PT, right? Page table can find out PT, right? PTBR base location. And then virtual page number is offset. So you know VPN, virtual page number, because that register contains this information. Okay. So hardware can find out PTE. Then the thing you have to do is locate corresponding page on hard disk. So the OS needs to figure out, okay, which page you need to copy, which page you want to access, right? This page, right? And third bullet, fourth bullet, choose a page to replace in the main memory. The thing is, what if the main memory is fully populated with pages? There are many different programs to run, right? So it is fully populated. All the pages, physical pages are being utilized. Right? That means you have to find out what? You have to find out victim. There are so many pages. 16 gigabyte divided by 4K, so 4 million. 4 million different physical pages. Among these 4 million pages, you have to find out victim. Which one do you want to kick out? Because you need to place this new page into the main memory. That means you have to sacrifice one guy. Okay, I want to remove this guy and place it here. Kick out this guy and place it here. Then you need some policy. Why this guy? Right? So which algorithm do you want to use? What kind of algorithm? LRU, right? LRU is, LRU is obvious, algorithm to select a victim, because LRU is what? Least recently used. Least recent. Probably that is least recently used. Or other 4 million minus 1 pages, got accessed recently. But this guy is not accessed. But implementing LRU, if you remember cache discussion, it's very expensive, right? Think about 4-way set associative, right? So 4 factorial, right? So that means 4, 3, 2, 1. 4-way set associative cache. Right? So you have a set, some set, then 4 candidates. So 24, different access history, right? But here, how many, right? 4 million different pages, then 4 million, right? Factorial, right? So you don't want to do that. You don't want to implement a true LRU, right? That is too much, right? So some, approximate algorithm should be used to select the victim. So that is in the PowerPoint, but I don't want to explain. That is too much probably for this class. So anyway, you need to find out the victim. To victim, place new page into main memory. Right? Then even worse, right? What if this page is dirty? What if this page, main memory is volatile memory, right? If you turn off the power, then data is gone. And then eventually that dirty page, let's say this dirty page, meaning you executed 4 instructions. 4. The new data is stored here. Store instruction, then the updated information is here. Then that page should be stored back to hard disk eventually. So that is third page. Then when you select this page as a victim, you have to make sure you store that into hard disk first. Then place new one. So if dirty, write the page to hard disk first. Okay, then place new page into the place. And then read request page. Okay, place that guy into here. And the second from the left, make interrupted, place run over. So we are in the middle of executing LDR instruction, right? In memory access stage, you got page fault. So that means when you come back after resolving page fault, you have to re-execute that LDR instruction. CPU, right? You have to re-execute that instruction from instruction batch, decoding, execution, and so on. So that is the last one. Start 14 instruction. That is the 14 instruction. 14 instruction. It's very complicated process. Any question about this? Okay, so that is about TLB, and let's stop this PowerPoint here, then jump into next PowerPoint. But think about this. Think about this issue. So it's some animation probably it is good recap, I think. So you have processor, CPU, processor. Inside the processor, Intel Core i7 or Cortex A9, you have a CPU core that is generating virtual address. And here you have TLB, translation cycle. Okay, and then probably you want to know this terminology. Memory management unit. TLB is placed inside the MMU, memory management unit. Okay, this hardware. So MMU is doing TLB lookup. The MMU hardware that is doing TLB lookup, then find out, try to find out translation information, generate physical address. So in this example, we assume cache is accessed with cache Cortex. And cache is implementing write-back policy. Write-back means what? Only cache will be updated. You execute the store instruction, then only cache will be updated first. Main memory later on, because we don't want to access main memory. Main memory is so slow, right? This guy is very slow. Even slower, right? Hard is super slow and slow, right? And cache is fast. Right? So we assume cache is implemented right back. Okay? So if you miss the cache, then you have to access main memory. So main memory contains page table. The operating system is creating page table. So at the beginning, everything is stored in hard disk, then that is placed in main memory on page basis. 4K by page is placed in here. Then you miss the cache, then from main memory to cache. It is a block-based transfer. Typical block size 64 KB. Cache block, right? 64 byte or 32 byte block. Right? That is typical size. Cache line size. Right? So block-based transfer from main memory to cache. Then what if you execute store instructions? Then only cache will be updated with new data because it is implementing write-back policy. Okay? And then when that guy will be placed in main memory, when do you think? New data is placed in main memory, when this guy is replaced. Cache is very small. Sometimes you need to bring in new memory block to cache. Then you have to select the bit tip. Right? When then bit tip is 30, then that bit tip is the 30 cache line will be written back to main memory. But eventually that should be placed in hard disk because the main memory is so still volatile. Turn off the power, data is gone. So when you place this guy to hard disk, when the page is replaced, dirty page will be replaced. That is the whole picture. Okay, that is the one. Then let's move on to exception. Let's play with a specific example with our Cortex A9, right? Page table and translation. Okay, this one, 성적, please. Okay, with virtual memory, what you have to do is, two things. First thing is address translation. That is primary region. Why primary function you have to implement, right? Virtual address to physical address translation, and the translation is based on page, right? Each page, and then with virtual memory support, it is providing some other important functions like this. In page table, you can do this. The page table contains translation information. Not only that physical page number, but you can have So you can have some attribute of that page, some property of that page, attribute or property. For example, the first page can be read only. This one is a read only page, and so it is all readable and writable page. So you can impose some restriction, some attribute, access permission, readable, writable, and also you can say, okay, this page is executable. Okay? Executable, executable, xe, executable, meaning you can do instruction patch. Instruction patch, then there is you want to execute your program, right? So you can set those property. Also, you can impose some restrictions like, okay, that page can be accessed only when you have enough privilege. For example, if you have PL1 privilege, you can access this page. If you have PL0, privilege level 0, then you can. What is privilege level 0 in user mode? Right? User mode. And privilege level 1 examples are supervisor mode and IRQ mode, right? FIQ mode, system mode, and so on. Okay? So if you have enough privilege, then you can access this page. Right? So you can. So the point is, you can set some attribute or property of that page. In this way, some protection is provided. On page basis, you can do this. So there is privilege information PL0 user mode in ARM, PL1 supervisor mode, system mode, IRQ mode, and so on. Okay, real stuff now. Okay, this one. 지수, 양지수. 현지, 박현지. 홍재. 낙원. 안 나온 사람 돗자리 가려. 오케이, 민지. 오케이, 하리원. 네, please. Okay, done. Okay, thanks. Cortex A9. Cortex A9 is providing 4 different page sizes. Okay? 4 different page sizes. Not only 4K byte, but 64 KB page, 1 MB page, and 16 MB page. But they are using different numbers. 4K byte, they call it small page. 64 KB page, they call it large page. Meg, section, and super section. Okay. Today we will talk about section translation. Section. Okay. Section is most simple. Section translation is most simple. Okay. That is why we want to talk today, and that is also basis for other page translation, super section translation, large, small page translation. That is a basis. Section translation. Okay, we will focus on section, 1 MB section translation. Okay. So virtual address in Cortex A9, 32-bit, and physical address 32-bit, 32-bit, and you have main memory. And then virtual address. Right? So let me draw, similar figure like this. Virtual address. You are creating 4 GB virtual space. So this virtual space and physical memory are logically divided into 1 megabyte. Here 4 KB. Right? 1 megabyte sections. Right? Here. So each one is 1 megabyte. 1 megabyte. Then the last one. So virtual section number 0, 1 megabyte. Section is 1 megabyte. Okay. So virtual section number 1. Second, 1 megabyte. And the last one is 4 gigabyte divided by 1 megabyte. Then 4K. Okay. So last section, virtual section number 4K minus 1. K is 1024. Okay. Then, main memory, same thing goes to main memory. That is logically divided into 1 megabyte physical section number 0. Okay, first one. Second, 1 megabyte physical section number 1, and so on. Okay. So they can be 32-bit. So you can install up to 4 gigabyte actual main memory. 4 gigabyte. Okay. Then the translation, right? So operating system is doing this mapping to run your application. Virtual section number 0 is mapped to probably physical section number 1. Virtual section number 1, probably that is mapped to, I don't know, here. For this. Physical section number 10. Okay, simple example. 10. Then so operating system also creating page table for this translation, right? In main memory. Translation information. Okay, so page table. Page table. You need to have how many PTs? How many PTs? For translation? How many? Can you? 4K, right? You have 4K different sections, right? 4K. Virtual section number 0 to virtual section 4K minus 1. So you need 4,096 PTs. PTs. Page table entry. Each one is page table entries. In ARM, I told you, right? TTBR register is pointing. Operating system should program this register, okay, to point the start location of page table. Okay. So then in this case, virtual section number 0 is mapped to physical section number 1. So what you have to record is here. So let's call this physical page number section and some attribute. So here you record attribute. Readable, writable, read only, some protection, and so on. Right? So physical page number. So here in this case, physical section number 1. So put 1 here. Okay. And then virtual section number 1 is mapped to physical section number 10. So in this entry, 10. Like this. Okay. Then this page table is indexed. You know the start location, right? And then how to find out translation information based on virtual section number. Virtual address 32-bit, right? Virtual address 32-bit. And we are talking about 1 megabyte section. That means last 20 bit is offset. 2 to the power of 20 is one bit, right? So there is offset within that page, within that section. Okay. And then upper 12 bit, there is virtual section number. Section number 0, section number 1, 2, this number, virtual section number. So, indexing, this offset, indexing, offset is, we use that language there. So offset, how do you do this? Right? How do you find out PT? Simple. TTBR plus virtual section number. And then each entry is 4 bytes in size. 4 bytes. So that is, so you have to do multiplied by 4. Okay, multiplied by 4 again, 2 bit left to shift. So hardware will do that operation to find out PT. And that information will be placed into TLB. And now let's talk about PTE now, right? We are curious about this PTE, right? Page table entry, right? Let me show you. So this is the information. This is the information about PTE format, actually. PTE format. Look at this section. If PTE is describing section in our example, right? Section. Each entry is talking about providing translation information for section, right? So look at this section. So PTE format, right? And super section PTE format. Next one. L2. Small page PTE format. Large page PTE format. So we have a format, right? PTE format. Let's go back to here. Look at this section. Super section. How do you differentiate these two? By looking at this. By looking at bit 18 and bit 1, you can tell. Okay, 0, 1, and that PTE is translation information. Section for section. Okay, and then 1 and 1, then PTE is super section translation information. Let's go to these pages. And last 2 bit is 0, 1, then large page translation information. 1, I don't care. Empty is don't care. Don't care. Anything is okay, 0 or 1. If the bit is 1, the small page translation. So section. Look at this. Here, this green. Green is physical section number. Physical address 31 to 20. So physical address 32 bit. 32 bit physical address. Then two sections, right? 20 bit is offset, same offset. This virtual offset and physical offset. It is actually concatenated. How do you generate physical address? So it is providing only physical section number. If we have a TLB hit. Page table, right? Page table is only providing physical section number. Physical section number. Physical section number. So page table is only providing a section number, not offset. Okay. Virtual section number 0 is mapped to physical section number 1. That information is only provided. Right? So 32 bit address. So you have 20 bit and 20 bit. That is physical section number. Okay. This physical section number is provided by TLB. If TLB hit happens, and then this offset is simply copied. That information is simply copied into last 20 bit. Okay. So again, PLB is only providing pitch correction number. And then 20 bit is simply concatenated attached, right? From this virtual address. Okay. So that is why PT inside PT you are specifying this pitch call address 31 to 20. That is pitch call section number. So, pitch call address 31 to 0. Then this one pitch call address 31 20 section number. The last 20 bit pitch call address from this pitch call address 19 to 0, 20 bit. Okay. So that information is contained in each PTE and some attribute. Okay, we are not going to talk about this attribute. Okay, so address translation is important. Right? So attribute is specified with those bits. Attribute NS, NG, AP, access permission, right? And TX, AP. Using those bit field, you can specify attribute or property. Readable, writable, privilege, executable, that kind of properties. Right? Any questions so far? Okay, with that said, let me show you demo. Okay, demo code. So that is the one. Then probably I need to show you TTBR information, right? Translation table base register. So that is a format, right? TTBR0 register. Here you have to specify start location of page table. And then the thing is, page table should start at there is some restriction. It cannot be start from any location in memory because page table size 4096 PTEs and each entry 4 bytes. So page table size, right? Page table is this one multiplied by 4 bytes, then 16 kilobyte page table size. Okay. So page table can be located at 16 kilobyte aligned memory location. So that this one should be 16 kilobyte aligned memory location. So example is 16K is what? 2 to the power of 14, right? So for example, that can be location can be 4 3 zeros. 4 3 zeros. Because 3 zeros 12 bit, right? And 4 is what? 1 0 0. So 2, right? 14 zeros. So 4 0 0 and or 8 3 zeros in that memory in those memory locations. Right? So that is 16 kilobyte aligned memory locations. Some more. Right? So that is one thing, because you can only specify by looking at, if you look at this register, you can specify only some x is 14, I think 14. Okay. Only 31 B2 14. And one more register you have to check is system control register. using this system control register, by look at this, last bit, M bit, MMU enable, MMU, right? So TLB is located inside hardware called memory management unit. So you need to enable that MMU to use TLB. So MMU enable is controlled by that register, system control register. Okay, two registers you have to have in mind. Okay, now let me show you demo. So demo is this one, MMU. So I created a project for you. In this demo, probably we don't have to have this interrupt vector table, but you know, I put our own interrupt vector table, and vector base register is set with this. Then, okay, translation information first, right? Translation table first. This one is page table. Example, a page table. So what we want to achieve with this, this 3 entries. So in our page table, we have only 3 entries. Dot word, right? This one, first entry. So that means here. So we have here 1, 5, D, E, 6. That is information in first PTE, first page table entry. Right? So page table entry starts from this label. Okay. So we are going to impose some restriction. Okay, page table, right? Page table should start at 16 kilobyte aligned memory location. How to make it possible? How to make it located at 16 kilobyte aligned memory location? So you need to play with the linker script. Check out this MMU table. Check out this linker script LD linker. Linker script is creating layout of your binary. You compile it. You compile your code, right? Compile your code, and final layout is generated. Final layout is generated based on the linker script. Okay, linker script. Check out this source code. So here, right? CAD MMU table that should be aligned at 16 kilobyte. Okay, 16384. That is 16 kilobyte, right? So that should start from that memory location. That is a directive. We are imposing some restriction. Okay, final layout, right? So linker script. That is one thing. Then let's talk about translation table, right? So we have three PTE entries. That word. That is actual PTE entry. Okay. So sec is variable. So you initialize sec to 0. Section actually, section number. Section number is 0. So 0, right? You replace this variable with 0. So first entry will be this number 15D6, this one. And second entry is what? Section is changed, right? Section is 0. Then you are adding this number 2 million, right? So second entry this information. So that means what? 2 million, right? So 2 5 zeros, right? So 5 hex number, right? So that means here 0x 2, then 15D6 DE6. That is the information, right? 2. So if you look at PTE, if you look at PTE for section translation, this one, you need to check out this, right? A section PTE format for the section, right? Look at this. So 0 to 19, okay, 20 bit. 20 bit is specifying attribute. Right? 0, bit 0 to 19. Right? So bit 0 to 19, 32 bit, right? 32 bit, right? PTE. Let me make it bit. Right? That is, 4 byte for 32 bit. Right? So if you look at that PTE format, right? First 20 bit specifying some attribute property. Okay, and then 12 bit. 12 bit is specifying virtual section. Okay, then check out this number 15. This one, the last 20 bit that goes to 15DE6. That goes to attribute. There is attribute field. Okay, so in this first entry, you are specifying virtual section number 0. Virtual section number 0, right? So second entry, right? 2. Second entry, you have same attribute. 15DE6, right? Same attribute, and virtual section number is 2. Okay. Then 2. So and then third entry before before setting up before this one, you are doing this. You are doing addition, right? This sec variable is what now 2 million, right? Initially 0. Then you are doing addition. So now 2 million. Then it is 2 million, right? Sec 2 million, and then you are adding one more 2 million, right? So 4 million. So 4. So third entry will be what? 0x4, same number, same attribute. 15, right? 15DE6. Okay. So that means we want to create that. Mapping, right? So virtual section number 0. Virtual section number 0, right? The first entry contains virtual section number 0's translation. So virtual section number, virtual section number. So we want to create that mapping. Virtual section number is corresponding to physical section number 0. Then it's talking about this. The first entry is talking about that mapping. Okay? And then second entry, right? Physical section number 2. Okay? Physical number section 0, number 0, 1. Physical section number 2. So virtual section number 1 is mapped to physical section number 2. Okay? So second entry is talking about that mapping. Okay? And the last one, virtual section number 2. So third entry is has translation information 4. Right? 2, 3, and 4. So 4. So that is mapped to. So we are creating that mapping with that page table, the simple page table. Okay, so then let's go to our assembly code. So system control register. So with the system control register, you are doing MMU enable, right? So simply read system control register information. So just read something, read. And where's TTBR? TTBR. Read TTBR. Translation table. And RC. Okay, read TTBR. Okay, so MMU disable. Okay, so here disable MMU. Disable MMU by touching a system control register. Scroll it down. So this is important information. So before, because we have 3 minutes left. So let me explain this way. So we are enabling MMU here. So before that, before enabling this translation, here with this translation, you are initializing memory, right? Initializing memory with that information. What information? You are storing something, right? R0, 1 million, R2, 2 million, 4 million, and the data you want to write. Then you are executing store instruction. So by executing store instruction, what you want to do is what? So 1 million location is this pitch call section. Okay. Then you want to write using that store instruction. First store instruction. R3 is 11, right? And you are writing 11 to that memory location 1 million. So here, the first location, you are writing 1, 1. Okay. And second store instruction. Second store instruction, second 4, right? 2, 2. 2, 2, 2, 2 million. Okay. So here, 2 million, right? Here you are writing 2, 2. And then third store instruction, you are writing 4, 4 at that location. You are initializing memory with that information. Okay. And then you enable. After that, you are enabling MMU. That means, you are doing translation. That is mapped to here. This one is mapped to there, and this one mapped to there. So in your program, what if you access? What if you read? So enable, then you want to read from location 1 million. Virtual. So you are executing LDR R6, R0, R6, R0, LDR R6, R1. This one is 1 million, 1 5 zeros. This one, 2 5 zeros. So you are reading from 1 million, you are reading from 2 million, right? But this one is virtual address. Right? So your virtual address 1 5 zeros, and second 2 5 zeros, right? Virtual address. Then because you enabled the MMU and page table is prepared for you, right? And now CPU processor will use that translation information to generate physical address, right? So the first load instruction, you are accessing 1 million, but TLB says, okay, 1 million 1 million location is mapped to 2 million. So 2 million, right? So physical address. So in response to that virtual address, physical address 2 million will be provided to actual memory. So in your program, you are accessing 1 million, right? But you end up accessing not this data, but this data. This location, physical 1 million location. 5 zeros, location 0, location 2 5 zeros, the location 4 5 zeros, but physical address, not virtual address. Physical address. So virtual address is generating 1 million. Then translation table says, okay, 1 million is corresponding to 2 million. So it seems like you are accessing 1 million. So it seems like you are accessing this data, but in reality, you are accessing this data. Okay. So second instruction, virtual address 2 million. So virtual address 2 million, and according to the page table, 2, right? 0, section number 0, virtual section number 1 and 2. Page table says, okay, that virtual section is corresponding to virtual section, physical section number 4. Physical section number 4. Okay, so TLB will provide 4 million. So it seems like your code, it seems like you are accessing 2 million, that data, right? But in reality, you are accessing this data. Okay, 47. Okay, so I'm going to show you demo next time. Okay, so we ran out of time. So show you, probably you run this code yourself, okay? Then you can find out. Okay, that is it for today. 안 되지. 패치 어버트는 여러 가지 경우에 생길 수 있는데 오늘 얘기했던 경우도 하나가 있고, 근데 오늘 얘기했던 거는 아닐 거 아니에요. MMU 이네이블을 안 시켰습니다. 그치? MMU 안 쓰지 않아요.
또 디버깅 모드랑 작동 하면은 중간에 터져버려요.
그러니까 그런 게 좀 이제 디버깅 하면서 고민도 많이 하게 되고 그러면서 여러 가지 막 이거 하면서 공부하는 거지 뭐.
시간에 데이터를 그러면 하드에 접근하고 하드에 접근하니까 IO 그러면 한대 스위치가 일어나지 않아요. IO를 하게 돼서 제가 링크에서는 IO 요청을 보내고 한대 스위치를 하고 다시 리드가 끝나면 그 로드가 끝나면 다시 한대 스위치를 해서 그 프로세스를 불러오는 거예요. 이 나와 있는 설명은 그냥 하나의 콘텍스트에
아니야, 맞아요. 그러니까 현재 페이지 폴트가 발생하면 현재 실행 중인 프로세스는 스탑을 시켜야지.
네.
그리고 이게 밀리언 사이클 걸리기 때문에 그 시간 동안 시스템은 다른 프로세스를 실행시키는 거고. 근데 그 실행시키기 전에 하드디스크에서 메인 메모리로 페이지를 카피하도록 시키는데 그걸 이제 DMA로 시작하고 다이렉트로 CPU가 관여를 안 하고 하드디스크, 이게 IO 자체 하드디스크다. 하드디스크에서 메인 메모리로 지가 알아서 트랜스퍼 하도록, 그리고 다이렉트 메모리 액세스라고 하거든요. DMA. 네. DMA 동작을 여기서 카피하는데 DMA 동작으로.
네. 아, 그러면 지금 여기 슬라이드에 나와 있던 설명을 보시면 이 페이지 폴트가 일어난 프로세스에 대한 설명이
여기는 뭐 OS 방법이 아니기 때문에 뭐 테스트 스위치 되고 현재 프로세스는 스탑되고 그다음에 새로운 테스트를 OS가 스냅해서 그걸 실행시키기는 하는데 그 1밀리언 세컨드 동안 뭐 놓을 수는 없어요. 그 시키기 전에 이제 그 가지들이 그리고 DMA 동작을 시키고 동작을 시켜서 시키고 그다음에 테스트가 끝나면 DMA라는 모듈이 있어, 하드웨어 모듈이. 시스템 컴퓨터에. DMA라는 모듈이 있었고 트랜스퍼가 다 끝나면 내가 인터럽트를 우리가 배웠던 인터럽트를 걸어서 그러면 나온 거죠. 아, 트랜스퍼 끝났구나. 서비스 루틴에서 읽어보면 알잖아.
네.
누가 걸었는지, 인터럽트를 누가 걸었는지 판단하고, DMA가 걸었구나. 그래서 보면 아, 트랜스퍼 끝났네. 그러면 다시 OS 스케줄러가 인보킹이 되고, 원래 폴트가 일어났던 프로세스, 페이지 폴트가 일어났던 프로세스 다시 굉장히 복잡한 과정을 거친 거죠.
그리고 제가 또 궁금한 게 저희 그러면 이전에는 캐시나 MMU도 활성화시키지 않은 상태로 코드를 짰는데 그러면 피지컬 어드레스 그냥 직접
버추얼 어드레스와 피지컬 어드레스 플랜 매핑이라고.
그냥 1대1 매핑
1대1. 그러니까 1밀리언이면 1밀리언 그대로 나옵니다. 플랜 매핑 그대로. 버추얼과 피지컬 어드레스가 그냥 같은 거예요. 얘를 이네이블 안 시키는.
근데 그러면 저희 제드보드 메모리 크기가 작으면 매핑이 안 될 수도 있나요?
그렇죠. 그러니까 지금 제드보드에서는 어떻게 되어 있냐면 메인 메모리가 512메가밖에 안 돼요.
그럼 그 이상은 안 되는 건가요?
그렇지. 여기 바깥에 이 영역 바깥에 메모리를 액세스하면 폴트지, 폴트. 폴트가 나는 거야. 그러니까 데이터 어버트라든지 우리가 익셉션 벡터 테이블에 보면 데이터 어버트 아까 얘기했지만 패치 어버트, 패치 어버트, IRQ 벡터도 있고 했잖아. 그게 하나 이게 일어나는 거죠. 존재하지도 않는 쪽에 존재하지도 않는 메모리를 접근을 하네? 그러면 폴트지. 하드웨어적으로.
근데 그 I/O 메모리 매핑 때문에 결국에 32비트로 돼 있기는 하잖아요.
메모리 맵 때문에.
네. 그러니까 저희 막 LED나 스위치 접근할 때도 로드로 하는데 그 주소가 다 1대1로 매핑이 돼 있다는 말씀이신 것 같은데 그러면 어쨌든 32비트 어드레스가 존재하긴 하는데 그 중에서 이제 512MB 범위를 넘어가는 걸 접근하면 어버트가 발생할 수 있어요.
그렇지. 우리 여기도 제드보드를 한번 보면 메모리 매퍼 제드보드 이렇게 하드웨어를 이렇게 회사에서 제공을 하면 이제 메모리 맵을 알려주거든. 우리는 이런 메모리 맵을 구현했다. 내려보면 이렇게 메모리 맵이 돼 있어.
네.
DDR의 경우는 여기서부터 여기까지 사용하는 거예요. 1메가부터 사용할 수 있는 거죠. 이 공간을. 실제로는 512메가바이트가 달려있기 때문에 이거보다는 요 반만 사용하는데 그리고 만약에 이 상태에서 이쪽 메모리를 접근을 했다. 만약에 4로 시작하는 그러면 페이지 폴트가 나는 거야. 폴트. 지금 존재하지 않은, 구현하지 않은 그런 그 디바이스를 액세스하려고 하면 하드웨어적으로 폴트를 그런 익셉션을 발생시키는 거죠. 그러니까 이게 메모리 스페이스가 완전히 다 사용되는 건 아니고 군데군데 사용되지 않는 그런 공간이 있어. 그런 공간을 액세스하려고 하면 CPU가 그러면 익셉션이 걸리는 거죠.
네네.
데이터 어버트나 프리페이지 어버트나 그런 게 걸리는 거죠. 이게 하드웨어적으로 그렇게 걸리도록 설계가 돼 있어. 존재하지 않는 공간, 비어있는 공간에서 접근하려고 한다. 그러면은 그런 익셉션이 걸리게 돼 있죠. 하드웨어적으로.